The theory of small oscillation is a very important and interesting topic of classical mechanics. It is found that when we have a large number or a system comprising of a large number of particles, and there is a to and fro motion of the particles of the system about their equilibrium position, then the theory of small oscillation is inevitable. As for example, consider a crystal lattice. In the crystal lattice, the atomic size oscillates about their equilibrium position, and the oscillation of one atomic site is related to its neighboring sites. So such a coupled motion is best treated through the theory of small oscillation. The other simple example is that two mass points, when placed on a horizontal table and they are connected by three elastic springs, then this is a coupled motion. And if we assume that the departure or displacement of the particle from their respective equilibrium position is not very high, then one can apply the theory of small oscillation. Before going to the subject the small oscillation proper, we shall first make a stability analysis. That is the stability of a system in terms of potential energy, or we define the equilibrium point. For equilibrium point, or configuration. For a single particle system, one speaks of equilibrium point. It is the value of x. If we consider x to be the single variable, then it is the value of x at which no force acts on the particle. And when we have a system of particles, then the state of the particle in configuration space is denoted in terms of generalized coordinates q1, q2 up to qn. If the system has n spatial degree, then at equilibrium position, at equilibrium configuration, then we do not speak about equilibrium point, we speak of equilibrium configuration. So it is the at equilibrium configuration, then we denote it q1 0, q2 0, etc. up to qn 0. This is the equilibrium configuration, and in equilibrium configuration, the force that acts on the particle is 0 for all I. So this is the definition of equilibrium position. So to say that equilibrium position is one at which the equilibrium position is one in which no force acts on a system. If we have a conservative system, then Qi is given by minus del V del Qi, and in equilibrium situation, if we represent this point by 0, then at equilibrium position this is 0, and we call it at Qi 0, the force, the generalized force at the equilibrium configuration. Before going further, we shall make the distinction between different equilibria. Equilibrium be two types, classified in this sense. This is called static equilibrium. And we have dynamic equilibrium. In static equilibrium, the system is in equilibrium state with zero kinetic energy, and at the same time the immediate neighborhood of the system is also in equilibrium. So there is no exchange between system and the surrounding. So it is the state
with zero kinetic energy, 0 Ke. It is also a state of zero kinetic energy. So here no force is exerted, no force is exerted by the surrounding. Here surrounding exerts balance force. In that sense, it is a this is stable, static and dynamic equilibrium. Example is that consider a ball at the bottom of a valley. This is a static equilibrium. And dynamic equilibrium, the example of dynamic equilibrium, say we have a ball on the top of a fountain. So the surrounding here exerts a balance force because the fountain tries to push the ball up, and on the other hand the gravity is pulling down the ball down. So these two forces are balancing each other and the system is in a state of dynamic equilibrium. There are other points of equilibrium, other distinction of equilibrium. They are denoted as stable equilibrium, unstable equilibrium, metastable equilibrium, and this is neutral equilibrium. Let us distinguish between all these in terms of potential. So say we have a conservative system. So the to keep discussion simple, we consider a system with one special degree. When the system is in a stable equilibrium, then if we displace the system slightly from its equilibrium position, then the system returns back to its original condition. Then it is called a stable equilibrium. Note the phrase that small displacement. If let us consider the situation that it is the potential energy curve of a system. So at this position, if we displace the particle slightly, then its potential energy increases, and to minimize the potential energy, particle comes down to comes back to its original equilibrium position, which is called a stable equilibrium position. If we displace the particle by a large amount, then we may set it over here. Then in that case, the particle do not come back to its then the particle does not come back to its equilibrium position. That is why we say when we displace the system slightly from its equilibrium position. So it is a stable equilibrium position, and this corresponds to a minimum of potential energy. Here we have another equilibrium position. This is an unstable equilibrium position, because if we shift the particle slightly from its equilibrium state, the particle never goes back to its equilibrium state. So it is an unstable equilibrium, and this corresponds to a maximum of the potential energy. So stable equilibrium corresponds to minimum of potential energy. Unstable equilibrium corresponds to a maximum of potential energy. Then metastable equilibrium state is this. Say the potential has a structure like this. So in this case, it is a zero curvature state. So that is to say the potential, the secondary here the second derivative is positive, here second derivative of the potential is negative, here the second derivative is 0, and if we displace the particle slightly from its equilibrium state, it may come back to this position, and it may not come back to its original position. So it is the metastable state. Actually, at metastable state, the potential function passes through a point of inflection, and there is another type of potential which is called the neutral potential. Say V is constant all alone. V is constant all alone, then the particle is indifferent to the position where it is, because there is no change of potential, and it is the neutral potential. Here V is constant. So it is inflection, and it is constant potential. So these are the different categories of potential. The theory of small oscillation that we are going to present will be applicable to a system when it is oscillating with a small amplitude about a stable equilibrium point. So if we want to categorize the equilibrium position, then from potential, then we are to first find out the equilibrium configuration. That is, we set the first derivative of the first derivative or derivatives of the potential to 0 to get the equilibrium configuration and then we shall make the analysis that whether the equilibrium configuration is corresponds to a minima or to a maxima. We confine or restrict ourselves to the discussion of stability to one-dimensional problem. For stability of more than one dimension, we have already discussed in connection with Lagrange's undetermined multiplier. So we consider few simple examples of potential and analyze the stability of the potential. In this juncture, we like to state that we shall consider few examples of where we shall study the stability of the system, and when we shall study the dynamical system, there will be plenty of examples which we will encounter, and we shall study the stability of it from another aspect, mainly that is the graphical approach. We first consider our stability analysis in 1D from a knowledge of potential, from a knowledge of potential. As for first example, we consider a harmonic oscillator potential. One is harmonic oscillator potential. We know that for harmonic oscillator, the potential is half kx square. If the then the graph of the potential is like this. It is the v of x, and this is x, and we know that it is a parabolic. From the graph, it is evident that x is equal to 0 corresponds to a minimum of the potential, and as for our theory that we have presented, the potential must have a minimum. So we first perform derivative of it. So it is kx, and v prime is 0 at x is equal to 0, and v double prime is simply k, where k is a positive constant and it is greater than 0. So V is minimum, so which indicates V is minimum at x is equal to 0. So it is a stable equilibrium point. So consider if we place a particle over here, it comes down to this. If we place it over here, it comes down there. So the particle approaches the x is equal to 0 point from either side. This is due to the tendency of the system to minimize its potential energy. As for second example, we shall consider an anharmonic oscillator. So harmonic oscillator is one for which potential is a pure parabolic one. For an harmonic oscillator, the potential has terms with power higher than x square. So second example is we are going to consider an anharmonic oscillator. Anharmonic oscillator. The potential function for an anharmonic oscillator, let us consider it is kx square minus 1 by 4 alpha x to the power 4. This corresponds to a situation when a force, the corresponding force is minus del v del x. So it is minus kx plus alpha x cube. So when the particle is experiencing a potential or a force which goes as x cube. So this is the famous example of anharmonic oscillator. So we first make the analysis of stability. So x prime of x is equal to kx minus alpha x cube. So v prime is 0 at x is equal to 0 and at x is equal to plus minus k by alpha square root. Here both k and alpha are positive constants. Now we'll go to the second derivative. This is k minus 3 alpha x square. So this is equal to k at x is equal to 0. And since k is 0, so this corresponds to a stable equilibrium position because double derivative is positive at x is equal to 0. Now coming to this point, at x is equal to plus minus k by m, v double prime is k minus 3 alpha, and for x square we write k minus alpha. So this is minus 2k. So this is minus 2k at x is equal to root over k by alpha. So since it is negative, it corresponds to a maximum of potential, and so it corresponds to an unstable equilibrium position. If we draw the graph of Vx, we see that at x is equal to 0, the potential is 0. V of x, and this is x. We draw the graph with k and alpha is equal to 1. So this graph corresponds to V of x is equal to half x square minus 1 by 4 alpha x to the power 1 by 4. So k is equal to 1, alpha is equal to 1. That we are choosing. At x is equal to 0, the potential is 0. So it is a 0 point. As x tends to plus minus infinity, the potential goes to negative infinity.
because of this term. So V0 is 0, V plus minus infinity goes to minus infinity. And if we say there are other points at which V is 0, so we can take it 1 by 4 x square commons, and then this is 2 minus x square. So there are two other points which corresponds to x is equal to plus minus root 2. So V at plus minus root 2 is 0. So there are 2 points. It is 1, 2, 1, 2, minus 1, minus 2. So there is a point at which the function is 0 value. So the graph of the function is like this. If we plot the graph of this function, the plot is this. So we see that it is a minimum point, so which corresponds to a stable equilibrium, and these 2 points are maxima, corresponds to maxima. So this is the stability analysis of an anharmonic oscillator. Now, as the third example, we consider an example which was set in our previous year in Calcutta University exam, and potential given, 1D potential given is V of x is equal to V of x is equal to x to the power 4 minus 4x cubed minus 8x squared plus 48x. So V prime is equal to 4x cubed 12x squared minus 16x plus 48. If we take 4 common, x cubed minus 3x squared plus 4x plus 12. Now we see if we put x is equal to 2, x is equal to 2, this is 8, this is 12, so plus part is 20, and if we put x is equal to 2, this is 3 into 4, 12, and 4 into 2, 8. So x is equal to 2 is a root. So we write x square x minus 2 because x minus 2 will be a factor of it. So this is x cubed minus 2x square minus x minus 2. So that minus x square plus 2x. Here we have minus 6x, so we must write it is minus 6x, so this is 6x minus 2, so this is 6x plus 12. So we have 4x minus 2, x square minus x minus 6, which is 4x minus 2, and this is x minus 3 and x plus 2. So the equilibrium points is for, so V prime is 0 at x is equal to plus minus 2 and x is equal to 3. Now we come to V double prime. V double prime, we calculate it from here, so it is 12x square minus
24x minus 16. So if we take 4 common of it, 3x square 6x minus 4. Now if we put x is so v double prime at x is equal to plus 2, we have this is 4 12 and this is 16. So this part is 3 into 4 minus 6 into 2 minus 4. So this is negative. This is equal to minus 16, it is negative, so so it is a negative point, and then plus 6 into 2 minus 4. So this is 20 into 4. 80. And if we put x double prime at x is equal to 3, we have 3 into 9 minus 6 into 3 minus 4. This is 20. So for we can decide the nature of equilibrium position from this analysis. V double prime is negative, means it is a point of maxima. So this is an unstable equilibrium point. It is an unstable equilibrium point, and these two are stable equilibria. Nextly, we should consider an example where the potential has maxima, minima, as well as point of inflection. The same example we have considered while maximizing a function of single variable. So the problem was the fourth problem, p of x is equal to x to the power 5 by 5 minus 3x to the power 4 by 4 plus 2x cubed by 3. So v prime is equal to x to the power 4 minus 3x cubed plus 2x square. So if we take x square common, this is x square minus 3x plus 2. So it is x square x minus 2x minus 1. So v prime is 0, v prime is 0 at x is equal to 0, x is equal to 1, and x is equal to 2. And v double prime is equal to 4x cubed minus 9x square plus 4x. So v double prime at 0 is 0, v double prime at 1 is, v double prime at 1 is 4 minus 9 plus 4 is equal to minus 1, which is 0, and v double prime at 2 is 4 into 8 minus 9 into 4
plus 4 into 2. This is plus 4 greater than 0. So we see that it is an unstable equilibrium point. This is a stable equilibrium point, and this is point of inflection. With this much of simple potential, we now go to two very physically interesting potential. One is known as Leonardo-Jones potential, which is in fact a spherically symmetric potential, but we take a model potential in 1D, the Leonardo-Jones potential. The potential function is like this. Let me first say a few words about the physical occurrence of this. We have heard that when two atoms, neutral atoms, interact with each other, the long range potential is the van der Waals potential. The van der Waals potential is the long range potential, which is a minus attractive potential, goes as x to the power 6 long range potential. This is the van der Waals part of the potential, and this van der Waals potential is always attractive, but we know that when two atoms come close to each other, there acts in repulsion between this, and the repulsion at small separation or separation less than equilibrium separation, the repulsion dominates and the two atoms are pushed away, and when they go away from the equilibrium, or when their separation is larger than the equilibrium separation, this van der Waals part dominates and the atoms are again pulled together, which is the molecular theory of atomic attraction and repulsion. The corresponding potential is known as the Leonardo-Jones potential. Remember that it is a potential in 3 dimensions, but we have taken a model in 1 dimension, where A is a parameter which has the dimension of length, as it is evident from this expression. So we first calculate the first derivative of it. This is V0 minus 12 A by x to the power 12 by 1 upon x, and this is plus 12 A by x to the power 6 upon 1 by x. So which can be written as, if we take 12 out, 12 constant out, this is minus a to the power 12 by x to the power 13 plus a to the power 6 by x to the power 7. So v prime of x is 0, means we omit this part and we have means that a to the power 12 upon x to the power 13 is equal to a to the power 6 x to the power 7, which says that x is equal to a. So this is the equilibrium separation. The v prime 0 means no force acts on it, and x is equal to a is the equilibrium separation between the two atoms. Let us calculate v double prime.
V double prime of x is from this expression 12 V0, then it is plus 13 a to the power 12 by x to the power 14 minus 7 a to the power 6 by x to the power 8. Now, so V double prime at x is equal to a is 12 V0, then it is 13 s square, and this is minus 7 s square. So this is 72 V0 by a square, which is greater than 0. So x is equal to 0 is a stable, x is equal to a is a stable equilibrium point. It is a stable equilibrium point. Recall the graph of this potential. Remember the graph of the potential. This is the x-axis. This is the potential axis. The graph of the potential is this. This is the equilibrium separation. It is the equilibrium separation x is equal to a when no force acts on between the molecule. If the separation is less than this one, this force is repulsive. The potential is positive, means the force acting between the atoms or molecule is repulsive, which pushes the molecule away from each other. And if we have large separation, the potential is negative, and at very large separation the potential goes to negative 0, so 0 minus tends to 0 minus. This is the graph of the potential, and since this point corresponds to a minima of the potential, minima of the potential which is evident from the mathematical analysis we have presented. There is another very interesting potential which is frequently used in molecules, which is known as the Morse potential. If we want to study the vibrational motion of a diatomic molecule, the most suitable potential, model potential, is the Morse potential. The Morse potential is defined as this. You see that at x is equal to a, the potential is a 0. At x is equal to 0, the x is equal to a, this is 0, and the potential is 0. This is twice V0, 1 minus is to the power alpha x minus a, and then derivative of it. So this is alpha times e to the power minus alpha x minus a. So v prime, this part cannot be 0. So v prime of x is equal to 0 means 1 minus e to the power minus alpha x minus a is equal to 0. That means say that x is equal to a. And if we calculate the second derivative of it, then firstly we derive this expression for v prime. We first derive the expression of v prime. So this is twice alpha v0, which are positive constants, and then we have e to the power minus alpha minus a minus e to the power twice alpha x minus a. This part is multiplied over there. So v double prime is equal to twice alpha v0
this is minus alpha e to the power minus alpha x minus a, and this is plus 2 alpha e to the power minus 2 alpha x minus a, and v double prime at x is equal to a is twice alpha v0. This is minus alpha, this part is 1 plus 2 alpha, so this is twice alpha square, v0 is 0, positive. So x is equal to 0 corresponds to a stable equilibrium configuration. If we draw the a plot of the most potential, it looks like this. This A part is the departure of the potential from the harmonic motion. sorry. If we draw a harmonic potential, this is the harmonic potential, and the most potential in this case is like this. This is the most potential, this is harmonic, and this is most potential, and this is the harmonic potential. Actually, if we try to study the vibration of a diatomic molecule by using a rigid rotor model which uses a harmonic potential, then we see that the energy levels are equispaced, the wave numbers are equispaced, and which does not allow us to explain the dissociation of a diatomic molecule. So in order to explain the dissociation of diatomic molecule, one relaxes the rigid rotor model and uses a harmonic oscillator model and uses the most potential, which allows the dissociation, and this constant V0 is related to the dissociation energy. So this much regarding the stability analysis from potential, from a knowledge of potential. That is, if we want to analyze the stability of a system from its from a knowledge of potential, then we first find the stationary points of the potential, that is the points at which the first derivative of the potential is 0. Then we analyze the nature of the potential from its knowledge, from its value of second derivative and the stationary points. We may encounter a situation where the second derivative itself is 0. Then we need to go to third or higher derivatives to get an idea about the nature of the stability point. For neutral equilibrium point, the potential only has the constant part, and all the higher order derivatives of the potential is 0 for neutral potential. That is, potential is a constant, and the particle does not feel any urge to return back to its initial condition or equilibrium condition when it is displaced, because in this case every point in configuration space is equally likely to the particle so far its potential is concerned. There is neither any maximum of potential nor a minima. The potential is flat all along. We shall come in the next class. We shall formulate the theory of small oscillation by considering a system having n degrees of freedom and which are described by its generalized coordinates.